Okay, by my watch, it's 12 o'clock. Good afternoon. I'm Matt Helmers here at Iowa State University with the Iowa Nutrient Research Center and the with Iowa SU Extension and Outreach, and fortunate to be involved with the Iowa Learning Farms. And as always, fortunate to be able to help moderate the conservation webinar series. So this week, we are really fortunate we're going to get to hear about bioreactors. Many on here, we know what bioreactors are, but we're going to learn some new information about pumped denitrification bioreactor system for treatment beyond subsurface drainage. Lindsey, God, I can't say anything today. Lindsey Hartfiel is a PhD candidate that's working with Dr. Michelle Sapir here at Iowa State University. So Lindsey, I'm going to turn the virtual floor over to you. As always, if you have questions, feel free to type those in the chat box and we will get those to Lindsey at the end of her talk.
Thanks, Dr. Helmers, for that introduction. As Dr. Helmers said, I'm going to be presenting on pumped denitrification bioreactor systems for treatment beyond just subsurface drainage. Okay, so just to give you a brief overview so you know what to expect in this presentation, I'm going to start by covering a brief introduction where, for those who are less familiar with bioreactors, I'll explain briefly what a typical bioreactor is in the context of Iowa and much of the upper Midwest, and then briefly what are some of the other applications of bioreactors. And from there, I'll move into our case study of a pumped bioreactor system here in Iowa. I'll start by covering our performance results prior to adding the pumping system, and then how we design and configure this pumping system, and then wrap it up with our future monitoring efforts. Okay, so here in Iowa and much of the upper Midwest, our agriculture is dominated by row crop agriculture, corn, soybean rotations. And a lot of the success of these row crops is through the use of subsurface tile drainage, which is essentially an underground network of pipes which work to remove our excess water from our row crop fields. Also in the soil is nitrate, which is an essential crop nutrient, but it's a negatively charged ion. And that negative charge means it doesn't like to stick to our soil, and instead it likes to move with water. So as we remove that excess water, we are often also removing nitrate, and that gets transported through our tile drainage and then released to our surface waters. And we don't like to see that nitrate moving downstream, as it has both human health and environmental impacts. In terms of human health, that nitrate is attributed to causing blue baby syndrome, and more recently it's been linked to several types of cancer as well. And in terms of the environment, here in Iowa, the nitrate ends up in the Gulf of Mexico and contributes to a hypoxic or dead zone, where aquatic life can't survive because of low oxygen levels. So to combat these issues with the nitrate leaving via the subsurface drainage, an edge of field conservation practice called a wood chip bioreactor has been used as part of our Iowa nutrient reduction strategy here. And this wood chip bioreactor, like I said, is located at the edge of the field. So it might take a couple rows out of crop production, but depending on the site, it might not even take any rows out of crop production. It takes our subsurface drainage and it routes it through the bioreactor. So our bioreactor is located underground and is essentially a pit of wood chips that acts as a food source for beneficial bacteria. So we have two gray boxes here. Both of these are called water control structures, one at the inlet of the bioreactor and one of the outlet. And these help to regulate how long the water is in the bioreactor for. Because it's bacteria that do the work for us to convert our nitrate into nitrogen gas, the longer the water is in the bioreactor for, the longer the bacteria have to work, the more nitrate we can remove. Also shown here, there's a red arrow with nitrous oxide gas. Nitrous oxide is an intermediate step in the denitrification process. So we might see a little bit of nitrous oxide, but there's a growing body of research showing that nitrous oxide in the grand scheme is pretty minimal, less than you would see from row crop fields. So it's looking like that's not a huge concern with these systems, but it might be something we see. But overall, the end product is nitrogen gas, which makes up the majority of our atmosphere. So this is harmless, and this is as a result, we have cleaner water leaving the bioreactor. So in the context of Iowa, the upper Midwest, this is how our bioreactors have been configured. Other places have tried some alternative applications of bioreactors. And briefly, some of these include pairing wetlands with bioreactors, using the bioreactors in ditches, diverting water from ditches to be treated. In Spain, they've been used to treat desalination brine that has high nitrate levels. They've been used for point sources like aquaculture treatment, as well as used to treat nitrate-laden spring water. If you're interested in some of these applications—
Give me 1 second here.
I will point you to a earlier Iowa Learning Farm presentation by Dr. Laura Christensen. This was from back in January, I believe, of 2021. And this presentation really covers a wide range of applications of bioreactors. So if you're interested in that, I recommend going back to that one, which is archived on the Iowa Learning Farms website. But these are not going to be the focus of my presentation today. Instead, I'll be talking about the alternative application of a pumped bioreactor system. So some of you might be wondering, why would we want to pump a bioreactor system? We've been using it for subsurface drainage. It works pretty well. Why would we want to change this? And our main reasoning here is that it would allow for treatment beyond subsurface drainage. So when we consider subsurface drainage, that subsurface drainage flow, tile flow, it subsides with the crop development. So as the corn gets really tall, it needs a lot more water, and the tile flow will often stop or be greatly reduced. So to demonstrate this, you can look at the gray and yellow lines here. That is the outflow from 2 bioreactor chambers. And I want to draw your attention to the end date for both years of flow. It ended in early July. And this is pretty common for many tile drainage systems. They will stop as the crop gets taller and needs more water. So then our bioreactor is not receiving flow, it's not being utilized. And in the case of this particular tile that feeds the 2 bioreactors here, it never starts up again. Once it stops for the year, once it stops in July, it never started again in the fall. So this could allow us to extend the bioreactor use to new applications, such as treating surface waters or irrigation waters that are high in nitrate. And another point here is that we're hypothesizing that this might actually extend the bioreactor life. The reasoning behind this is that research is starting to show that the wood chips that are subject to greater fluctuations in the saturation level break down more rapidly. So if we could use a pumping system, this could potentially allow us to keep a more uniform level of saturation in the bioreactor, more consistent flow going through the bioreactor, and keep it saturated for a longer period of the year. And in doing so, we're hypothesizing that this could potentially extend that bioreactor life. So with that, I'm going to move into our case study of a pumped bioreactor system here in Iowa. Here you're seeing an image of this particular bioreactor site, which I'll describe a little bit more here. So this particular site is what we call a dual chamber bioreactor, which means it's essentially 2 bioreactors that are connected in parallel. So looking at the bottom of the screen, you can see the incoming drainage. And then there's 3 water control structures that we refer to as being inlet control structures. So the first is our main inlet, and this is where the water is either routed into our bioreactor chambers to inlet A or inlet B, or if we have enough flow, some of it might be bypassed. And this is so we're not backing up the flow into the row crop fields, and we're not forcing the water through the bioreactor where we could create preferential flow conditions. So then it goes to inlet A, inlet B, and we refer to these 2 bioreactor chambers then as chamber A and chamber B. The water will flow through the bioreactor, so on your screen from the bottom to the top of the screen, where it will go to the 2 outlet control structures and then is released back to the surface waters nearby. Also, as part of this system, we have 9 randomly located sampling wells that we can collect samples for different water quality parameters. And their units are given with respect to the bottom left corner of each bioreactor chamber in units of meters as XY coordinates. I'm guessing most people are probably more familiar with units of feet. So to give you some context, these bioreactors are 34 feet wide by 124 feet long each, which is pretty large for bioreactors typically installed. In terms of our monitoring at the site, this started in 2019, and it has included monitoring for nitrite plus nitrate, which I will probably refer to just as nitrate from here on for simplicity. And then total organic carbon, we collect samples monthly, and then we monitor for flow rate, water level, temperature, and dissolved oxygen. And we monitor for all of these things from all the water control structures and our sampling wells. For the purpose of this presentation right now, I'm going to focus in on our results of the nitrate and our flow rate. So you've seen this one once before, but this time I want to draw your attention to the blue line at the top of these graphs. This is the design flow rate for both of those bioreactor chambers. And then our yellow and gray lines are the outflow from chamber A and B respectively. Now you can see that we have not actually reached the design flow rate at this system. And most often we're operating well below the design flow rate. And our average flow rate is below 10% of the capacity actually in those 2 years. I didn't include 2019 data here as we changed our flow monitoring method. So that year I have not included just for that reason. But again, I want to remind you that these bioreactors are driven by microbial process. So the longer the water is in there, the more time they have to do their work, the more the nitrate can be removed. I also want to point out that most often chamber B has greater flow at the system. We have the water control structure set up to be the same, but just based on how the site is and how the grade of the site is, chamber B typically gets a little bit more flow, which you'll see come into play in the next couple slides. So chamber A, now I'm showing you nitrate removal over time. So we collected samples from all those wells as long as there was flow going through the bioreactor. And I used an inverse distance weighting statistical method to predict what the nitrate concentration was throughout the whole bioreactor chamber. So here, inlets at the bottom of the screen, outlets at the top. So we're flowing from the bottom of the screen to the top of the screen. And at the inlet, we have higher nitrate levels above our safe drinking standard of 10 milligrams per liter. And by the outlet, for all 3 years, we have pretty much complete nitrate removal happening, represented by that dark purple color. Especially in 2019 and 2021, that removal happened very early on in the bioreactor chamber as well. Then when we look at chamber B, in 2019 and 2020, we also saw complete nitrate removal happening. And in 2021, there was high nitrate removal, but we did not get quite to that complete nitrate removal. And these are all representing the median concentrations. So based on these results from 2019 and 2020, we added in monitoring for sulfate and dissolved greenhouse gases. So sulfate we wanted to monitor because as the nitrate is completely removed, the bacteria start to look for other things to reduce, and the next easiest thing for them to work to reduce is sulfate. And we don't like to see sulfate reduction for 2 reasons. The first being our bioreactor is intended for denitrification, so then the wood chips are being used for something other than their intended purpose. But the second larger concern is that sulfate reduction has been linked to methylmercury production, which is a human health concern. Methylmercury can bioaccumulate in the environment through the food web. So us at the top of the food chain who consume those aquatic species exposed to that methylmercury, we can be exposed to high levels of methylmercury. So that's undesirable to see happening. And then we also monitor for those dissolved greenhouse gases. So we're not monitoring these greenhouse gases from the surface of the bioreactor. Research is showing the amount of greenhouse gas leaving the top of the bioreactors is pretty small, quite minimal. The majority of greenhouse gas that you would see is actually in the dissolved phase, so it's in the water. So we monitor for nitrous oxide. because that's that intermediate step in the denitrification process. And it actually has a global warming potential about 300 times stronger than carbon dioxide. So because of that, it's an important greenhouse gas to monitor. So we monitor that. And then as well as methane. Methane can also be produced once that nitrate is removed. So monitor for that one, which has a global warming potential about 25 times stronger than carbon dioxide. So here, now I'm showing chamber A, the median concentrations for our different pollutants across the bioreactor chambers. So I'll start on the left-hand side with the nitrous oxide. Again, inlet's at the bottom of the screen, outlet at the top. So we can see higher nitrous oxide levels at the inlet, lower nitrous oxide at the outlet. So this is a good thing that we're seeing. The bioreactor is not producing nitrous oxide. That's good. Then in terms of the nitrate, you can see it's removed the nitrate, which is good. But we have a little bit of mixed feelings about this. We don't want all the nitrate to be gone because, again, that can allow for the sulfate to be reduced, which is linked to methyl mercury production, and it can allow for methane to be produced. So some mixed feelings on the nitrate. Then looking at the sulfate, you can see that once that nitrate was gone, it allowed for that sulfate to be reduced. So we have sulfate reduction, again, linked to methyl mercury. This is a bad thing. We weren't happy to see this. Then looking at the last pollutant here, methane. Again, once that nitrate was removed, it allowed for that methane to be produced at higher concentrations. So this was undesirable. Now, when we look at chamber B, I said this one has higher flow rates. So the water is not in the bioreactor for as long. So starting on the left is the nitrous oxide. It had pretty consistent levels across the whole bioreactor chamber, but maybe ever so slightly a little bit higher concentrations at the outlet. So I wouldn't say this is terrible. There wasn't a huge difference in concentration from the inlet to outlet, but still not great, slightly higher. Then looking at our nitrate, this was again not completely removed. In chamber B, it removed a lot, but not all of it. So this was good. And then because not all that nitrate was gone, this limited the sulfate reduction. So also good, and it also limited the methane production. And the sulfate and the methane were held at the same scale as chamber A, so you could see the difference in how these two bioreactors were behaving based on the flow rates they received. So this led us to consider, how could we improve our bioreactor system? We don't want to see that sulfate reduction or the methane being produced. So this led us to consider a pumping system. So our first thing when considering this pumping system was the site selection. So could we potentially improve that bioreactor's performance by adding the pumping system? So with that comes, was there a source nearby that could provide enough flow during periods of low or no tile flow to supplement our tile drainage fed bioreactor? And with that, these bioreactors are used for denitrification, removing that nitrate. So in the source that we were interested in pumping from, was there enough nitrate to make this feasible? So this site is located right alongside Big Creek. So we've grabbed some samples from the creek since 2020. In 2020, we only grabbed 2 samples when we were just starting to think about, hey, maybe pumping is a possibility. And those 2 points are at the very top of the graph with concentrations at or above about 12 milligrams per liter. So this is above the safe drinking standard. It would be high enough that we would consider this to be feasible. The concentrations are actually quite comparable to the tile drainage that's coming into the bioreactor already. Then 2021, this was a drought year. So you see a lot lower points. We really weren't surprised by this. It's the lighter blue color. Because the creek because of the drought, the creek stopped flowing or wasn't flowing very much at all. So this is why we have those lower concentrations. We weren't really surprised or really alarmed by these concentrations. And then this year, the couple of samples that we've been able to get analyzed already, they're again much higher, around 10 to 12 milligrams per liter. So based on these results, we think we have a source of water that, as long as it's not a drought, will have enough flow and nitrate to be reasonable to be pumping from. So the next thing we wanted to consider as part of our pumping system is that it would be flexible. This is the first pumping system we're trying out, that we want to be able to modify it if needed. So we're not burying the pumping system under the ground like the rest of the bioreactor is buried under the ground. So we're going to pump directly into our water control structures with all the pumping stuff above the ground. Then the next component is we want to be able to monitor the flow. At the 2 outlets, we monitor for the flow using vented pressure transducers, and this would give us the total amount of flow going through the bioreactor. But we also want to know the breakdown of what was from drainage versus what was from the creek. So we have flow meters as part of our pumping system to allow us to monitor for the flow from the creek. Then one of our last major components is that we want to filter out for large particles. So we have a large coarse filter to kind of keep out some of the debris from the creek. We don't have a fine filter, as we figured the amount of sediment might kind of clog that filter very often and have put a strain on our pump. So we have kind of accepted that we might have some sediment coming into the bioreactor. And then lastly, we got a water use permit from the Iowa DNR to be able to do this pumping into the bioreactor. So here is showing a schematic kind of over the top of the bioreactor what this pumping system design looks like. So in the creek, we have a float with a filter to draw our water in. And we have then a pump, and that will be located inside a job box. And the flow will then be divided from the pump and split into our 2 inlet control structures, Inlet A and Inlet B. With this, we'll be metering the flow again, so we know how much is coming from the creek, and we can regulate that flow using a valve for each of those as well. So here, we have not gotten this fully installed yet. We've been dealing with some supply chain shortages. And also this year, we've actually had quite a bit of periodic rainfall. So we've had pretty good flow coming to the bioreactor this year. So at this point, we have not gotten this fully installed, but we're hoping to get this installed in the next week or 2. But here we have this set up so you can get a rough idea of what this is going to look like. So here we're looking at the level of the creek. You can see that float where the filter will be under the water there, drawing the water in. Up on the top here, there's a platform where we are keeping our pump located in a job box. And then here's another image kind of giving you an overview with where this is with respect to the rest of the bioreactor. It's kind of hard to see the 2 smaller inlet control structures that we will be pumping into, but here, if you can see my arrow, I'm not sure, but there's a red flag, and Alex, a fellow grad student, is sampling from the inlet structure at that time. That's Inlet B, and then kind of behind the job box is Inlet A. So that is how the roughly showing what this pumping system will look like when it's fully installed. So then lastly, I'll discuss some of our monitoring after we get this fully installed. So we're going to monitor for flow rate, water level throughout the bioreactor, as well as temperature. And then in terms of our water quality monitoring, we are going to continue our monitoring for nitrate, sulfate, the dissolved greenhouse gases of nitrous oxide and methane. Continue with the total organic carbon. We've also added in monitoring of pH, and then E. coli is something that we've been monitoring. In the drainage, the E. coli levels have been very low, but the creek has pretty high E. coli levels. So once we are pumping, we also plan to explore the bioreactor as a possibility to help to reduce pathogen levels in the bioreactor. So with that, I'd like to acknowledge a few individuals for all their help. So I'm going to start with Leanne Long for her help analyzing the majority of our samples, Natasha Hoover, who managed the site early on and passed it on to me once I got my feet under me at Iowa State here, and then fellow water quality research lab members, especially the undergraduate research assistants who helped to collect the numerous samples, and Dr. Andy Craig, who has been a big help in getting this pumping system design and in our efforts in getting it installed. Then I'd also like to thank Doctors Tom Eisenhart, Morgan Davis, and Stephen Hall for their help with greenhouse gas analysis, and then Dr. Marshall McDaniel and Stephen Potter for their help with total organic carbon analysis. And last but certainly not least, I'd like to thank our funding sources. And this project is funded partially by an Iowa NRCS SIG grant and also a USDA NEFA grant. So big thanks to the USDA, NRCS, USDA NEFA for funding this research effort. With that, I will open it up for any questions. Feel free to type those in the chat box. Also here is if you need the Certified Crop Advisor continuing education units, you can email Liz Ripley at the email address shown there with the information requested. And then also highlighting next week's webinar for those who are interested in attending next week's.
All right.
With that, I'll turn it over to Dr. Helmers.
Okay, thanks, Lindsay. Thanks for excellent presentation. And we already have a few questions in here, but if others have them, feel free to type them in the chat box. So the first one, kind of on the design, is this dual chamber design specifically for research purposes, or was that what formulated that design? Because normally most of them I've seen, and I think that this person has seen, are single chamber designs.
Yep, this was designed by the Iowa NRCS. There's a 14-inch tile that was feeding the bioreactor. They were expecting a lot greater flow rate because of that 14-inch tile. But it appears that the tile itself was actually over-designed for the drainage area. So we're not really sure if it was supposed to be added into another drainage area that we're going to add on to it, but it was designed based on the size of the tile, not necessarily for research purposes.
Now it's becoming useful for research to have both those, I guess. So
yes.
The next one is actually next couple are kind of on the mercury question, but the first one, do you know if there's mercury in the water or the wood chips?
Yeah, we're not entirely sure where the mercury would be coming from. I know that mercury is pretty, it's deposited through the atmosphere, so it can be deposited in the fields. So we're thinking it might be coming in the tile drainage, but it also could potentially be in the wood chips. It's not something, that has been actually researched or explored.
Okay. Yeah, so this one, how do you power the pump?
We have electrical installed at the site. It's nearly completely installed, should be done by the end of this week.
Okay, and then this one is, have you sampled mercury directly or do you plan to in the future? And second, have you considered monitoring iron in addition to the sulfate?
We have not considered the iron, but I know that, yes, that is also linked to the methyl mercury production. So that's something that, maybe we'll look into and see if that's something we're capable of analyzing for in our lab. What was the other part of the question?
If you've sampled for mercury directly.
We did collect just on one date last year because we're interested in submitting some proposals to look into this methyl mercury stuff more. So we got just 2 samples on one date from each of the bioreactor chambers. And there was methyl mercury production in the one bioreactor on that one date.
For the one that was had so much less flow?
Yes.
Okay. The next one is, and I'm assuming this will, well, no, I think it's a yes, but I'll ask you. As your work proceeds, will you be assessing the economic efficiency of the pump design as compared to non-pump to compare the cost per pound of nitrate removal?
Yeah, it's something we haven't done yet, but it's definitely something that I think would be beneficial to weigh out if these pumping systems are feasible on a larger scale.
We still have time for some other questions. Oh yeah. Oh great. We just had 2 come in. Why were the monitoring wells installed at random locations instead of at consistent spacings across the width and length of the bioreactor?
I wasn't here as part when they installed the sampling wells, but I know they wanted to get the interest in the like spatial dynamics. So across the length and width. And I'm guessing maybe it was just randomly placed rather than uniform across both the length and width, just as a feasibility in collecting samples, reduce the number maybe a little bit.
Okay. Okay, we're getting some great questions. Okay, so do you think there's any chance to use solar power for pumping these types of systems?
Yeah, there is another, as part of the funding for this, there's another pumping system that was installed in Illinois, and they did use solar power. So that one, they're figuring out the kinks on that one because it's solar. There's some variability in the flow rate versus in the day versus the night.
Okay. And so you kind of talked about this, that there's a filter to remove maybe any big material before it goes into the bioreactor. But are you worried about the sediment accumulating in the bioreactor by pumping from the creek?
Yeah, as part of this, yeah, because with a finer filter, we think it would get clogged pretty often. So we chose to not include a like fine filter to filter out that sediment. But yeah, we are interested to see how much sediment gets pumped in and how that affects the bioreactor. So we're also planning to do a tracer test before and after the pumping system to see how that changed the bioreactor.
Any thoughts or projections on how much more end mass removal you might get with the pumped system over a non-pumped option?
I don't have a good guess at this point yet, because we haven't really, this bioreactor, since it's always been such low flow rates, we don't have a great idea of what its performance is going to be when it has closer to the design flow rate, but I do expect it to be a lot more on a mass removal basis than it has been.
And I guess this is, do you foresee pumping systems being the sole source of water for bioreactors rather than tile drainage?
I think that pumping systems for different applications, I think it could be a sole source, especially if you have a really consistent high nitrate level source that could be pumped.
A lot of bioreactors may be in a position where there's no water to be pumped from, right? So
yep.
not all of them will be positioned right next to the stream. The next question is kind of getting at the specifics of the pumping system, but it indicated the intake hose from the stream seems to be a bit small compared to how sized the creek is. Is the primary goal of this research to reduce nitrate in the nearby creek, or just to, I guess, maximize end removal by this specific bioreactor?
Yeah, we know it will, be able to reduce a little bit of the nitrate in the creek, but yes, the creek is much larger, has a lot more water moving in it than will be moving through the bioreactor. But our main focus was to improve the bioreactor conditions, so we weren't having the sulfate reduction, methane production, those things happening anymore. So to improve the mass removal of nitrate in the bioreactor.
And that's kind of getting at how would pumping as a sole source change the design of a bioreactor, or would it?
I don't think it would necessarily change the design a whole lot. It wouldn't necessarily maybe even need the water control structures at that point. If you have you're going to pump at a consistent rate, maybe you don't need an inlet water control structure, because you wouldn't be bypassing. So there might be some slight changes, but I think overall the bioreactor itself would stay pretty much the same, I think.
Yeah. This kind of getting back at the sediment question. If sediment accumulates in these bioreactors, are we worried that this would lead to short circuiting that might cut down on the retention time or kind of use of the full bed of the bioreactor?
Yeah, that's something that, we're interested in exploring. So that's part of why we're doing those, the tracer test at the start of the pumping to see what the bioreactor flow was like in the bioreactor before we added the pumping system. And then after we have ran the pumping system for probably 2 years, we'll do a tracer test to see if it's already changed the flow dynamics in the bioreactor. So we'll keep a close eye on that and see if that sediment is a big problem.
Great. Still time for more questions if anybody has them, but We will, for those that need a CCA CEU, reminder, get your information to Liz Ripley. The email is ejucums@iastate.edu by today at 5 p.m. With your name and the name you entered to watch the webinar and your CCA number. And then again, a plug for next week, talking about interactive cover crop. Dr. Peter Caverga with Iowa Soybean Association will be on talking about that. If there aren't any other questions, I want to thank Lindsey. And I think that useful information today, but also then hopefully we can get you back on at some point to talk about the results from when you start pumping into this. And as we talked before, at least so far this year, we're getting more flow so that you have some water to pump out of Big Creek. So really, thank you a lot, Lindsey, and I hope everybody has a great rest of your day and week, and look forward to virtually seeing many of you next week as well. So everybody take care.